welcome to the third session of our Aerospace Workshop by SimScale featuring EUROAVIA. I think you already know the procedure. Before I start to actually dive into our today's topic, I would like to make sure that the audio is working for everyone fine and you can hear me loud and clearly. Guys, you know this. If you can hear me, please press the raise your hand button to show me that audio is working for you. Great, I already see a lot of fans. Seems that everything worked this time. Very nice. In the case, for some reasons, the audio connection should drop for you, or you got problems with your computer-based audio, we also provide, as you know, toll-free audio service numbers. You just have to call one of these toll-free numbers and enter this access code here. And then you're able to listen to the sound via your phone. Great. Okay, let's start. Today we are in our last session, and we will today take a look at compressible aerodynamics of an aircraft. And first of all, I will just summarize the most important things about this workshop and webinar session. Then we will take a look at the results from last week, from the homework of last week, and then we will talk about compressible aerodynamics. I will show you for sure how to set up such a simulation yourself using SimScale, and also tell you some very important things about the fundamentals which we really need to understand to use simulation in a productive and effective way. Yes. I think most of you already joined the previous session, so let's make it very crisp. You know, the idea of the webinar is really, or this workshop series, is to enable interested persons who are interested in aerospace industry to get first insights about engineering fundamentals and simulation fundamentals. And in contrast to the last session, this session we will talk a little bit about fundamentals. As I mentioned, it's very important to understand some basic things to be able to create a high quality and nice aerodynamic simulation. And in the case you have some feedback, we already received some feedback, but if you, in the case you have something you really want to tell us about our product, what is good, what we could better, please reach out to us. And yes, this is the last session, as I mentioned. It will be recorded for sure, like all the other sessions, and you can access the recording from tomorrow morning, I think, on our website and our forum. In the case you have a problem with the simulation, guys, please use first the forum. I got a lot of direct messages, which I'd for sure answered all, but the reason why you should use the forum is that some questions were asked by several people, and if it's in the forum, it's easier for those people to access the answers, and if people have similar problems, they don't have to write a new email. Great. Okay, then let's dive into our today's session, and first of all, as I mentioned, we will review the last session. Some of you had problems with audio during the session, therefore we had to re-record the session and had some delay. I really apologize to everyone who had this problem, and we really try our best to deliver these webinars in a very good quality. Please consider also that we have like 100 people attending this webinar, and sometimes if our third-party tools are not working, there's nothing we can do. So again, sorry. And yes, when we are talking about the homework, something very important. You usually have like 1 week after the session to submit your homework. And since there was this problem with the recording, we decided to extend this deadline. So you can extend your homework for the last session till Sunday 12 p.m. Okay, now let's dive into it. So here you can see basically what your homework was. Last session we talked about structural simulations, and I showed you how to set up a structural simulation of such an aircraft structure. And your homework was, or your task was, to investigate or to simulate 2 different design variants. And the difference between them was that we added in the first design, in the design 2, we added stringers, And in design number 3, we added stringers and additionally added fillet to high stress regions. And your job was to perform for each of these designs 2 load cases and to investigate by this which improvement is the best or how this design improvement can help to increase the stability of the wing. Yes, we had, as I mentioned, 2 load cases you had to investigate. So first of all was the bending load case, where we fixed this face of the wing and of the structure and applied on the whole lower surface a pressure load. And another load case was a torsional load case. There we applied 2 pressure loads, one on the upper front half side and one on the lower back half side of the surface. And it was for sure again fixed in all directions here at the surface. And you therefore had to create 3 meshes and 6 simulations. And you can access, as you know, our step-by-step tutorial. So it's not very complex to redo this simulation yourself. But you will learn a lot. And the best thing is that this homework will really show you what is the great thing about engineering simulation. But I would say let's take a look at the results. And if you have questions, just write them into the question box, and I will, and this time, answer all questions related to the last session before we start with our live demonstration. Okay guys, first of all let's take a look at load case 1, the bending. Here you can see in this graph I plotted the pressure load against the displacement of the wingtip here. So we had a point here which we were which we tracked virtually somehow, and as you know, we were not applying only 1 load but 4 loads within 1 simulation. And first of all, because a lot of people asked me, 1.8 meter, isn't this much too high? Isn't this a much too high deformation for a wing? And first of all, you should really keep in mind that the final load, this 100% pressure load, is much higher than what would happen in a real flight scenario. So what would be more realistic for a maximum load during operation is something in this range between 0.25 and 0.3. And here you can see for the initial design, the design number 2 with the stringers and design number 3 with stringers and added fillets, how the displacement is depending from the pressure load. And what we can see, first of all, very obvious, is that there is not a big difference regarding the behavior on the bending for design 2 and 3, so these additional fillets are not impacting this very much. But you can see a difference in general between design 1 and 2 and 3 here. And the reason for sure is that when we apply a bending load, we are really increasing the stiffness with the stringers. So the main effect for the bending load is the stringer. And now let's take a look at all different load states. So here you can see the stress distribution on the 3 designs without any load. For sure it's then 0 everywhere. And here you can see the wing. So what you can basically here we have the wingtip, so this is there, and we are looking from this direction. And I only visualized the feature lines, the edges of the 3 designs, put them together, and now we can take a look at every load step, what happens. So so here we have our first load step, and as you can see, there seems not to be much stress, but what you can immediately see is that here you can have already this difference between the blue one, which is design now initial design and the yellow and gray one, which are here. So here we have already a first difference. And if we increase the pressure load more and more, we already can see the stresses. And let's go a step further. Yes, and here you can see actually how the stringers are helping to improve the bending behavior. Because if you take a look here, it really, until the stress becomes dark blue again, it takes up till here. And here, it's here, so it's before it. So, and what basically happening is that the stress is now going also through the stringers, and it reduces the overall stress, and for sure also the displacement of the wingtip. And if we now take a look at the final load stage, let me just clear my sketch. Yes, then you can also really see here the difference in bending. So this is a difference about 0.2 meters. Well, and there is something very important related to the bending, and the reason why we need to add the fillets even for the bending, because it has not a big influence on displacement as we saw, but here you can see design 1, design 2 and design 3 for maximum load, bending load, and here is the area where the initial stringers meet the ribs. And with the initial design you can see stress distribution is quite okay. But with adding the additional stringers, we have a high increase of stress in this region. And this is because the forces are now going another way through the material, and we have a lot of stress and force here, and this can really create a problem. And by adding the fillets, we can solve this problem, because the cross section is not changing so fast. And we don't have some, and you know, this sharp edges are really an invitation for stress, and so this helps us to reduce the stress. And these are two different things you should really keep in mind. In the end, for the aerodynamics, we're only interested in the displacement, because the displacement is changing, you know, the structure of the geometry of the wing. But if we take a look at the structural integrity of the airfoil, for sure we want to make sure that there is no hotspot of stress and that the overall stress is not too big in the part. Yes, next let's take a look at the torsion load case. And here we have in the end 2 points we took a look at. So a point here, let me just change the... Here we have a point, the front tip point, which we are looking at right now. And it's again the same. So here I'm plotting the displacement magnitude of the point here against the relative pressure loads. As you know, this torsion load has 2 components. It's a momentum we are applying on the wing, a torsional momentum, and both of them are scaled the same way and have the same magnitude, both forces. And if we now take a look, you can see a much bigger difference. So in blue again, we have here how the displacement depends on relative pressure load for this point, and you can see it really becomes quite big. So we have like 0.18 meter difference. So this point gets up by 0.18 meter. And adding the stringers helps to reduce this, and it really has a big impact on torsion, the stringers. Not really by the half, but by, yes, I mean, it's nearly reduced it nearly by 30%. And with the aid of the additional fillets, we even drop this more to 30%. So just, and this is something you should really keep in mind. We have not really changed the amount of material used. Maybe it's less than 5%. change of material, and so less than 5% increase of weight of the structure, but we have like dropped the displacement or the torsion by more than 60%. And now let's take a look for different load cases. So again, and here you can again see all three wings compared. Now we are looking from this side, and now you can see how it bends for different. So this is how our, by the way, how our front tip goes up and how our back rear tip goes down. And you can see this blue one represents the initial design, and even for a very, if we look at the very small pressure load in this area, the other bars, the design 2 and 3 are nearly not changing. And even if we increase, you can see how much more design 3 is bending. And I think here you can really see it. This one completely changed his face in the end, completely changed how they are looking. I mean, it's like a wave right now, and you can see it even here, while design 2 and 3 are still really looking like a wing. And this would be a big problem. Just imagine that would happen in reality. That would mean your wing is not working anymore. Finally, we can also do the same for the displacement of rear tip, and here we have quite similar results. The only difference is that if we're looking at the rear tip, it seems like the fillets would have a negative impact. And that is not really true, because what you should not forget at the end, that even with a small displacement here, I'm like changing the whole reference of the wing. And the reason in the end, or last thing we could optimize by adapting the fillets, for example, would be to put the torsion rear tip or the displacement magnitude of the rear tip for design 2 lower by modifying the fillets, for example. Yes, there's a last thing I would like to take a look at at the displacement compared, maximum displacement compared, and stress compared. So here we are not, if we go back, here bending we had like maximum of 1.8 meter displacement, and here it's less, because here we are not looking at the displacement at this tip point, but we're looking at the bending. And what you can see here compared is displacement, and for all three designs, so this is design 1, design 2, design 3. And here you can see how displacement and in y direction is changing for yes, the maximum is changing. And here you can really see, if we take zoom here, we can see that it really has this small impact for bending, but this very high impact for torsional load. And this is much more interesting. Here we take a look at the maximum stress in the material. And here we are only looking at the final load case. And here you can see something which looks really strange, because beam with stringers seems to have a higher von Mises stress than the initial version. And we already talked about the reason, because we had this changed way of force going through the material, and by adding the stringers we can even reduce it. And this, finally, in combination of all 4 graphs we took a look at, this proves that the design number 3 is really the best. Yes. Okay, before we start to talk about our today's topic, if it's now time for questions. If you have a question related to the last session or the homework, please ask it now. Or for sure you can also ask it in the end, but I think now it would make much more sense. Okay, then let's take the next step And as you know, today we are going to talk about aircraft simulation. And this is what we want to do today during the demo. We will simulate free flight of a large aircraft with a fixed velocity. So we will simulate Mach 0.35. And so just let's take first of all look at the case setup. So in the end, it's quite similar to what we did in the first session. Because we're interested in aerodynamics, we have to simulate the domain around the aircraft, not the aircraft itself. And we have an inlet where we know the velocity distribution here, because this is the velocity we want the aircraft to fly with. We have an outlet, here we know the pressure, and we have other boundaries which we will assume as slip-free walls. And before we actually start to dive into the simulation setup, we should talk about some fundamentals which are really important. Because external aerodynamic simulations, especially for such big and fast-moving objects, are really complex. And one thing we have to talk about really is turbulence. And I think most of you are students, so you may hear about turbulence, but there are also some people maybe who never talk too much about it. So let's first of all talk about turbulence and why it's important. Okay, what is turbulence? I know there are a lot of definitions in the world, but if you really put everything in a nutshell, you can say turbulence is a chaotic change of field values in space and time. And that sounds maybe very abstract, but it's quite easy. Let me show to give you an example. For example, when we have a laminar flow, which is somehow the opposite, it would mean that we assume that if the flow is in a stable state, let's say we have the square here, and we have this flow around the sphere. These are the streamlines. Oh, I'm not an artist, sorry. Again, we have here the sphere, and then we have a streamline around the sphere. And with chaotic change means that we cannot say, even we cannot say that these values are still constant. So turbulence means that, and best visualization for this is that your flow is looking like this. You have different eddies with different scales and sides, and you don't know, that means chaotic. You cannot predict what will happen next to the flow. And if you take a global look at the flow, it may stay constant, but if you took a look at the inner fields, you see a lot of chaotic change of all field values. And with field values, I mean everything: pressure, temperature, flow velocity, and so on and so on. And I mean, to make it clear, let's take a daily life example. One important thing about turbulences, I mean, we can talk about when we expect turbulence, but we cannot say what is the reason of turbulence, because turbulence is not really fully understood. It's still one of the major physical problems where we actually not really know what is happening. But what we can do, we can somehow quantify turbulence, and we can somehow and we know somehow what is the criteria for turbulence. So let's take a look at a very easy example. Let's imagine you have this water flow, and through this valve you control the flow rate. And for very low flow rate, for a low flow velocity, the water flow coming out of this will really look like this. And if you take a look at this, it will not change its shape, for example, and it will be laminar, so you will not see any recirculations or stuff like this. And if we now increase the flow rate by opening this valve more and more, we see that as higher the flow rate is, as more chaotic seems to be the flow. So it change transient its shape. So you would then see like it's changing his diameter here of the flow, and yes, as I mentioned, as higher you increase the flow rate, as more turbulence will occur. And this is something you can really test with in your bathroom yourself. And this is something very important. So there is something we can say right now, that increasing the flow rate or the flow velocity will also increase the turbulence. Now let's imagine we take this stage here, which is already turbulent, and replace the water by oil, which has a much higher viscosity. And what will happen then, that the flow seems again to be laminar, and we can't see any turbulence. And maybe now it reminds you on something you already heard at class at university. Because if we take a look at the impact of flow rate or velocity, the velocity represents the initial forces, and viscosity represents the viscous forces. So it seems like if a turbulence occurs dependent of the ratio between initial and viscous forces, and this is a formulation for the so-called Reynolds number. So if you take a look at this formula, what you can see here, U is the flow velocity, which is depending on the flow rate. We have L. L is a characteristic length, and in this case, for a pipe, you would take the diameter, and you have also density here, and this is divided by the viscosity. And this Reynolds number is very important in fluid mechanics because it's a kind of dimensionless number which can give you two information. First of all, for different applications, there are different so-called critical Reynolds number. For example, for a pipe, it's 2300. And you can assume that a flow stays laminar until this critical Reynolds number is reached. And applied to this, it's quite easy. Here, the Reynolds number, for example, critical Reynolds number, for example, for a pipe flow like this is approximately 2300. And at this stage, you know, viscosity is constant, density is constant, length is constant. We are increasing the Reynolds number with increasing the flow rate. And that's the reason that here the flow becomes turbulent, because it means that here the initial ratio of initial forces or viscous forces changed in a way that it's higher than 2300, and that's the reason why we have a turbulent flow. And here is the same. Here we have a constant flow rate, but we change viscosity. And because viscosity is increasing, the Reynolds number is dropping, and the flow becomes again laminar. Another very important thing about the Reynolds number, it allows you to compare flows or aerodynamic tests. So that's the reason why Reynolds number is very important for wind tunnel testing. And two objects, or let's say two scaled models with the same Reynolds number will have the same behavior. And that's the reason, for example, why you can use a 50% model at wind tunnel testing. Okay. I mean, I hope everybody now got a basic idea of what turbulence is, and to put it in a nutshell, turbulence, again, chaotic change of field values in space and time, and we can decide if a flow is turbulent or not by using the Reynolds number, which is representing the ratio of inertial and viscous forces. Now, let's take a look at something else. I told you turbulence is chaotic change of field values in space and time. And now let's feel this phrase with some images and some... okay, let's assume I have a turbulent flow. For example, this one. And I would just put here a probe point and measure at this point the flow velocity for constant boundary conditions. So my flow rate going through the valve is constant, viscosity is constant, everything is, and I'm now taking a look at this velocity here. And what you will see then is that the velocity is not constant, it's fluctuating, and this is this chaotic change of field values. And this is not only for velocity, it will be the same for all other transport properties like pressure, temperature if considered, etc. And so when you have a turbulence flow, even for a steady state case, you have no constant velocity. And what we can do now is to average this velocity, for example, and say, okay, this is average velocity in this time. And then we can express the time-dependent velocity in this point as the sum of the average velocity plus an oscillating part. You can really imagine, so this is constant, and this, or this, or this is your fluctuating component. And I mean, this is a big problem, because here we have this fluctuating part, or this oscillation part, occurs really on different time and length scales, which means the fluctuation can be very in a high frequency and a low frequency, and it can be very and the magnitude of this oscillation can be big or small, and you have a lot of different scales. And to numerically remember how CFD is working, that we try to numerically solve this Navier-Stokes equations, that will be a high effort, because if you really would like to solve turbulence based on the Navier-Stokes equations like this, you would have an incredible high effort to solve all scales, which would mean if you have a very, very small time scale, like let's say 1 nanosecond, here in this graph, you have to use a time step of 1 nanosecond. And then you can imagine how many time steps you have. And additionally, as you imagine, all the times right now, even in the first session, we did steady state simulations, which means we did not take a look at, we only take a look at the average flow field. And with this approach, you can only do transient simulations, because your velocity is in any case time dependent. But there is a reason for sure, which is called turbulence modeling. Instead of really calculating this turbulence, resolve all the scales of turbulence, which would be a lot of work to do, and which is, by the way, only possible even on the largest computers in the world for very easy applications, we just say, okay, ignore the oscillation. We say our flow has only a mean, flow quantities have only a mean value. And then we are okay, but what's about the turbulence? Because you should, in the end, shouldn't forget, if we ignore these oscillations, we will get a problem with our conversation equations. And there is a very easy approach. We replace oscillations and say, okay, we have to add something else to minimize the error, or to account the oscillations on another way. And so we introduce the so-called turbulence viscosity. The this is in the end nothing else that a way to model transport and dissipation of energy neglected by averaging. Because you should not forget, the turbulence is transporting energy. And in the end what we do is, there is three principles of conservation. We have for each of these principles an equation in CFD. We have momentum, energy, and mass. And what we do is we replace the viscosity in this equation, in the moment equation, by a new viscosity called effective viscosity. And one part of this effective viscosity is the real physical viscosity, so the actual viscosity of our flow, and we add a turbulent viscosity. And this viscosity is not really a viscosity. It's not physically existing. You cannot measure it because it's not there. But this, let's say, new viscosity can be calculated with external models. That means you don't have to resolve all scales. You can use additional transport quantities. And in the end, we are using a turbulence model, which is calculating turbulence with some simplifications on a macro instead of a micro level. And we calculate with the help of this, or the aid of this turbulence model, we can calculate this turbulent viscosity. And then we again close our equation system, and we are able to also consider turbulence without solving all scales. And this is something very important you should really keep in mind. This is a huge simplification. And it's not generally valid. And to be honest, if you would ask someone who's really involved in turbulence research, he would say this is not true. But the simplification is still good enough for most of the cases and allows us to simulate also complex high Reynolds number, high turbulent flows with limited amount of computational capacity. Okay. One very important thing when we talk about turbulence just to understand what I mean with different scales. So let's take a look at this. Let's imagine this is kinetic energy of the flow, core flow far away, for example, from the wall. And what is happening is in the end that turbulence is dissipating this kinetic energy into the energy of the turbulence. And so at the beginning we have large scale eddies, isotropic eddies and anisotropic eddies. And later on this vertices are dissipating in smaller ones, and so on and so on. And so in the end it's just a way of converting energy. And here you can see basically two things which are characterizing turbulence. The energy in the turbulence, so the energy of the turbulence at any point, like the velocity of the flow at any point, and how much it is dissipated. And for this, by the way, there are a lot of turbulence models out there, but the most industry relevant turbulence models are so-called two-equation turbulence models, which are based on two additional transfer properties, which are for sure not existing in reality. It's just a help for us. And one of them is the kinetic energy of the turbulent, and one other is the dissipation rate. And right now what we're doing, we're adding these two transport properties to our existing ones. So instead of only pressure, velocity, temperature, we also have the kinetic turbulent energy and dissipation rate, and that helps us then to calculate turbulence on an easier way. And there are different two-equation models, and they are all based on this approach of having these two transport quantities, but some of them are dedicated for special applications. So on SimScale we have these three turbulence models available. first of all is k omega SST, which we will use in 99.9% of all cases. And I will tell you the reason. K omega SST in the end is a mix of so-called k omega and k epsilon turbulence model. And the difference between these models is the way dissipation is modeled. So K, that's the reason why both of them have K in the names. The turbokinetic energy is modeled the same way, but the K epsilon model is using a so-called turbulent dissipation rate, while the K omega model is a so-called specific dissipation rate. And I don't want to go too much in detail, but in generally you can say K epsilon is performing very good far away from your wall in the let's say free stream, but not performing very well in the near of walls. And K omega is performing very well in the near of walls, but is too sensitive for pressure gradients, which means that outside of the wall, so in the free stream, it can create bad results. And what K omega omega SST is doing in the end is switching the turbulence model locally depending on different criteria. And there's a last thing we should talk about when we're talking about turbulence modeling. It's again the boundary layer. And as you know, we talked about in the first session, the boundary layer is defined as a very thin layer, like between the physical surface and the free stream, and everywhere where flow velocity is smaller than 99% of the free stream, we're talking boundary layer. And the reason why the boundary layer is so important is that we have or we assume or we know that flow velocity on the wall is 0, because we have a stick condition there, which means you get such a profile for the velocity, and which is also changing flow if you go down the stream, because the friction between these layers is increasing more and more. And therefore you need a special kind of meshing in the near of walls, which is also very important when it comes to turbulence modeling. And the idea is to have very flat cells here, because we have only a high gradient to the surface normal, and this helps us then to solve this gradient as good as possible with the minimum amount of cells. And yes, very important, without layers your simulation will not be realistic, especially turbulence modeling will not work, and you should never apply these layers on non-physical walls like inlets and outlets, because there the gradient is very small in normal region. It would make absolutely no sense. And the question now is, which is very important, which cell size or which height do I need here to resolve this layer perfectly? And since this is a hyperbolic profile, we would need to solve it accurately. We would need a lot of cells here, really a lot. So this is just a schematic sketch. And this means that if you would just only use turbulence model and prism layers, you would have 100 millions of cells from the boundary layer. But there is a good trick which is called the law of the wall. And this, guys, is also very important, so please listen carefully. Like more than 100 years ago, a lot of researchers, one of them very known is Kaman, investigated what is happening exactly in the boundary layer. And to put it in a nutshell, what they found out is that if you use dimensional quantities for velocity and wall distance, you find out that there is a specific way to describe velocity close to the wall in the boundary layer, the dimensional velocity close to the wall, as a function of the dimensional wall distance. And dimensional wall distance in this case means really the distance between the wall and the point. So to calculate the dimensional wall distance, for the first cell, you take the distance from here to here, and for the next cell from here to here, and so on. And if you take a look at this graph, it's a logarithmic representation. You can see that we have like it's linear in this viscous sublayer. Then you have a kind of buffer layer. And then here you have a layer where it's logarithmic. Don't get confused because it's a curve. It's still linear because it's only a curve because of the way this logarithmic representation. And the good thing is that since in this viscous sublayer it's linear, it is not really important to have a lot of cells here. And now it's a very smart idea. This viscous sublayer can be also described by this law of wall, which means what we can do is to put the whole viscous sublayer in one cell and model the velocity profile, this profile here, instead of calculating and resolve it, which will result in less cells. And the only requirement is, and it depends on the simulation tool you're using, you need a dedicated number for y plus for the first cell. And if you want to use the law of wall, this value should be between 30 and 300. If you don't use the law of wall and really resolve the boundary layer, you need a y plus of 1 for the first cell, which will make all your cells smaller and result in a lot of more cells. Great, okay, then that I would say we got a good introduction into the fundamentals we need, and right now we can start to actually create our first simulation. Are there any questions related to the fundamental stuff we discussed before? Seems there are no questions, so we can really dive into simulation. As you know, today we want to do external flow simulation of an aircraft, and there are some very important things you should really keep in mind. First of all, we said we have a Mach number of 0.35, and I think most of you know what the Mach number is, but basically the Mach number is the ratio between the velocity or the speed of your object divided by the speed of sound. And speed of sound in gases depends, by the way, let's call it A, is depending on kappa, which is isentropic exponent, density, and pressure. And so, the Mach number just shows you the relation between your velocity of your object and the speed of sound. And since we have a Mach number of 0.35, we have to calculate compressible. I know, in theory, only a Mach number of 1 is the supersonic, or larger than 1 is the hypersonic. But even for lower Mach numbers, starting from 0.2, 0.515, we already have compressible effects, and therefore we have to do a compressible simulation. But let's start with it, and then I think you will really see what is important. I have prepared here a project including the geometry. Let's open it. And this is also the project I will provide you with later on for the homework. And so here you can see there is a CAD model, and yes, bounding block length makes sense, and also the direction length, so it seems to be the right scale. And as you can see, this model was much simplified. So first of all, it's a symmetric model, so therefore we only use a half body. And for example, the jet engine were replaced, and there's just a hole, and you can see that there are not only a few number of single faces. And last time, I think on the last homework, or the first homework of this aircraft cabin, you used automatic meshing. This time we have to do manual meshing because the geometry is too complex, and we really want to spend cells only there where we need them. So we already created face entity sets. I prepared it already, so which will later on help us when we are going to find mesh refinement. Let's just take a look at this set. So one set, for example, includes all these small edges. For example, the rear edge of the wing. We have also added all fins to a face set, and even the fillets which are connecting these two areas. Yes, and right now we will start to create our mesh. So we click on create new mesh, and this will add a new mesh project to our SimScale control window. Now we have to first of all select the geometry we want to simulate and save it. And next we can add a mesh operation. As you know, there are a lot of different operations, and we will use this hex dominant parametric, which means that we want to create a hex dominant mesh which is only usable for CFD, and define all parameters ourselves so that we have full control. And as you know, the meshing tool we're using, SnappyX Mesh, is based on a very intelligent and unique approach. Instead of building this mesh from bottom to top, we start with the background mesh, which we refine and later on snap on the surface. So the first thing we have to define is our bounding box, our fluid flow domain. So save this mesh operation, we'll complete the meshing tree, and first thing we'll add here is the bounding box, so the fluid domain around our aircraft. And I use 0.001 instead of 0 for xmin to avoid that, because of numerical problems. You should not forget that this is a CAD model was imported, and by using this a little bit larger, it's just 1 millimeter number, we make sure that the symmetry plane will really align with the bounding box. Well, let's say a maximum of 175 meters in x direction. Sorry, wrong way. In y direction, min point of -300 and max point of 300. And for that direction, this is in this direction, -350 to 250. And now you can see our fluid domain around the aircraft, which is quite fine. Next thing we have to specify is a material point, because right now we are meshing really the whole domain, but later on we don't want to have any fluid cells inside the aircraft, and therefore we have to specify which point should be inside the flow and which outside. And here basically you can use every point which is between the outer surface of the aircraft and the surface of the bounding box. I will use this point right now, and just a trick, try to avoid using numbers like 16. It's better to have values which which are not like this, because what can happen in some very rare cases is that this can result in a problem, but you don't have to care too much about this. Now if we save the material point and show it, you can see the point here, and this point is inside. Okay, next, now we have defined the size of our domain, but we also need to define the initial mesh cell size. And for this we have to go back on this operation tab in the tree and add here the number of cells in each direction for the background mesh. And yes, let's use these values. And if you know, calculate yourself, you will see that the cells are not isotropic. That means the size of the cells is different in each direction, but overall it's around 8 meter for level 0. That means this is the coarsest cells or cell size we can use. And now we can start to define our refinements, because right now if we would not touch this mesh, what would happen is that we would have a mesh with a cell size of nearly 8 meters, which is much too coarse. It's good for the outer region because there we don't need this accuracy, but we need a much more finer mesh in the near. And we can do two things. First of all, we can do surface refinements later on and apply different smaller cell sizes, for example, for the thin edges or the wingtips. But we also are interested in the flow field and around the aircraft, and therefore we will create refinement boxes where we can refine the mesh for the whole region. And first of all, let's create an outer cylinder around this aircraft with this reference point. And it's in the end very easy the way you define a cylinder. You're just defining reference point, an axis, and a radius. Save, and now we can see here. And this is how our outer cylinder is looking like. We will also add an inner cylinder. Let's call it cylinder outer. We will also add an inner cylinder with the same reference point, and we have just a smaller axis. Sorry guys, I mixed up in and outer cylinder for sure. This is the outer cylinder and this is our inner cylinder. Well, next thing we need is additional refinement around the wing and fin tips, because there we expect to have eddies. You know this because we have a high and a low pressure zone, and this will create eddies. So create a new cylinder, first for the wing, and these points you have to find out using your CAD model, CAD system, or try and error, but this can take a lot of time. And now we have here a refinement zone for our wingtip, and we'll do the same for the flap tip. Fin tip, sorry. Yes, I already added the reference point. Now let's add the axis. And then we have additional refinement zone here. And if we would now, for example, let's show all of them at the same time. Now you can really see what is our refinement concept. So we will refine the mesh a little bit in this whole big cylinder. Then we will have additional refinement with this inner cylinder. And we will have a much more fine mesh in these critical areas at the tips of fin and wing. Great. Now we are done with creating this refinement zones, these bodies. And next thing we will do is to create the actual mesh refinements. And yes, first of all, we create a so-called surface refinement, which we just called surface large. And here we select the whole body and apply a level of 7. And level of 7 means that the initial cell size of the background mesh, which was approximately 8 meters, will be splitted 7 times. So level of 7 means a element size of of nearly, let's say, 6 centimeters, which is not bad. But as you know, this 6 centimeter is maybe fine for this area here or here, but it would be much too coarse for the wing, for example, or the fins. Therefore, we will add different additional surface refinements, and here is a very important thing again. When you apply several surface refinements, there's automatic mechanism behind SimScale that will identify the highest refinement level, so that you can, for example, in this case, for example, let's first of all create for the thin edges in refinement. And since they are so small and have a big effect, we will have a cell level of 10 here. But these edges or these surfaces are also included in solid 1 because they're part of the whole solid. But SimScale or the Hexaeder Mesher is smart enough to take only the finest refinement. So if you have multiple refinements, it's not a problem, but only the finest will be executed. Edges. Let's do the same for the fins. Again, a surface refinement. Select the pre-created face sets. And here we need even a finer mesh, cell level 10, which corresponds to a cell size of 8 millimeter. Finally, we need a surface refinement for the fillets. With a size of 9 to 9. Here we have 8 and not 10, sorry. And now everything is fine. So we will get now different mesh sizes on the surface. And next we have to create volume refinements, region refinement based on the geometrical primitives we created before. So let's start with the region refinement for the wing fin. There's 3 different modes. We can mesh all cells inside this cylinder or outside, or with a distance from the surface of the cylinder. We'll use inside. And yes, here we can choose wing and tip. And we will have a refinement level of 9 there. So very, very fine. Click on save. And then we will create the same for the outer region. there we want to have a cell size of, or cell level of 2 for the inner region. And there we want a cell size of or cell level of 3. Finally, we'll add 2 more things. First of all, a so-called feature refinement. The reason why we need this feature refinement is, as you can remember from the first session, this mesh is, we're creating this background mesh, applying the refinements, then we're deleting the inner part, and then we have like a stepway structure here. And the stepway structure later on is removed by snapping the face to the face is the elements to the surface. But because of this Cartesian cutaway approach, it can happen that edges are lost and sharp edges become fillets. And this refinement type extracts all feature edges of this geometry based on an include angle, and then we can define an additional snapping and refinement for these edges. And there we have 2 parameters. The first parameter is which so here we can manipulate which surfaces will be or which edges will be extracted, and then we can define a refinement level. So here 8, and from a distance 0.2. It means that 0.2 meter away from up to 0.2 meter away from this edge, the cell level should be at least 8. Save. And finally, we will create a layer refinement. And here are something is very important. There are 2 kinds of layer generation. First of all, we will select all faces, because here the inlet and outlet are part of the bounding box, so we can select all surfaces of the aircraft. And then there's different parameters. First of all is the number of cells, so the number of flat cells, then the expansion ratio, so that's the grow parameter. Then a final thickness, and this final thickness can have 2 meanings: relative or absolute. This is something you can control in the operation menu. Relative means that these 2 numbers, or that the absolute values for the final, so the total is the final thickness of the last layer, and the minimum thickness are calculated relatively to the surface mesh size, which makes it very easy to have a high quality mesh. But you can also use absolute values, but I would recommend relative. And if you ask yourself now, where do I know the values which I need to reach the y plus I need, you can calculate it basically. There are some equations. And what I would suggest is in the end to play around, because you can also take a look at your y plus and just to play around with these parameters. Okay, and finally we have to change some advanced settings. First of all, we will use 16 cores, and then we will start to modify, first of all, the snap control. And the first thing we will modify is this one. Sorry, first of all, the castellated mesh controls. It's the number of cell between levels. We'll increase it from 3 to 4. And the meaning of this parameter is quite easy. Right now, when we have a change of required mesh resolution, for example, because of a refinement region, he would not make directly switch from, let's say, level 3 to cell level 5, but he would find some buffer layers between it to have a smooth, to make the mesh more smooth. And we will use more of this smoothing layers between refinement zones, because we have a large difference of refinement, because of a very coarse mesh in the outer region and a very fine mesh in the inner. So that will help us, but for sure it will also increase the number of cells. Next thing is the snap control. This is about this step of snapping, which I told you, when the mesh is going to be snapped on the surface after deleting the inner part. And here we will change implicit feature snap to false, because we want to do explicit feature snap. This means based on this feature criteria we gave here. And then there's one thing or two things we will modify regarding first of all regarding the quality control of the mesh, and here we will reduce the number of layer iterations. So creating this layer is an iterative process, and we just say we want to make not more than 15 iterations to reduce the computational effort. And we will change here our mesh criteria. This is, in the end, has no impact on the final mesh, but it changes when SimScale gives a warning because of meshing problems. So we will reduce that, which means that we even want to have a much more high quality mesh. Oh, this was wrong. Here. What we have to change is the minimum good thing is if we did a mistake we can just jump back. The values changed back automatically. Okay. And change this to -12. And the reason is that for this incompressible simulations we need a much better mesh, and therefore we want to get warned if our mesh is not so good. For an incompressible simulation the standard values will be fine. Right, and now we're done, and we can start the actual mesh creation by clicking the start button. This will take some time, and therefore I have already prepared a case with the same geometry, the same mesh setting, and a finished mesh. Great. So here you can see the mesh, which is finished. Or first of all, you can see here that is finished, and then we can take a look at the mesh log. And the mesh quality, this warning here is not important. Important is what is here. And here you can see finished meshing without any errors. The reason why we have these two different checks is that this is really checking fundamental things which are necessary for a successful simulation, while this mesh check is checking some things which are nice to have but not really mandatory. Okay, so we have overall, as you can see, 3.6 million cells, and now you can see here is a mesh. So let's first of all hide the bounding box surfaces. And then we can see here the surface mesh. Okay, then let's first of all do a quick wrap up. And take a look of what we've actually learned. Well, first of all, I showed you again how to import a project. I mean, that sounds very, very stupid and easy, but it's the way you have to import later on your own project for your homework. And the next thing which we did was creating a parametric hex dominant mesh. And in contrast to last time, this time we really did everything manually, starting from bounding box definition, creating geometrical primitives for refinement zones, which we created later on, and also layers. And like every time, there are two things we could take a deeper look at. First of all is CAD cleaning and repair, but there we have a good webinar recording you can consult. And even for manual meshing, there are a lot of ways to play even much more with your simulation, with your mesh criteria and these mesh parameters. And yes, then I would suggest to go back to the mesher, because there's just one thing I would like to show you. I mean, we took a first look here at the mesh, and you can really see how the refinement was automatically applied. So here you can see the influence of the refinement box on the different surface mesh levels, or especially here, for example, that we even, here you can see the effect of this feature snapping, that these features were refined. But we can also take a look inside the mesh using our mesh clip filter. And yes, let's make a cut on that direction. Click preview to see. For sure we have. And now we're going to create a cut here. Apply, that can take some minutes, since everything has to be computed. And then we can take a look at the mesh and really see how powerful this meshing tool is. And yeah. And this is something you should do every time you're interested in your final mesh result, to take a look inside and see how the inner mesh structure is looking like. Since this can take up to 1 or 2 minutes for such a large mesh, let's already start with the simulation definition. And the next step now, after we have our mesh including layers, is to set up the simulation itself. So click on Create New Simulation, Analysis Type Fluid Dynamics Compressible. We have want to use a K omega turbulence model, steady state simulation. Click on Save. And first step is to select the mesh. Just click here on Save. Then the mesh will be added to the project tree. And the first thing we will do right now is first of all to create topological entity sets. Because after, there are two kinds of topological entity sets. You can create sets for the CAD model and for the mesh, but they are not linked. And we also need another kind of topological set here. Because first of all, we'll create a set called symmetry for the symmetry surface of the model. And then we have also a sidewall. We have here inlet, an outlet, top, bottom, and if we know height, all of the surfaces, the only remaining surfaces are the walls of the aircraft, and we can select them by using select all, create a set. Great. And yeah, next step is first of all to define the material property of the fluid domain. Therefore, we have to add the material. We will assign it to the only fluid flow region we have, our mesh. But instead of defining this material ourselves, we will again take a look at our material library and select air. Now this is also done, and we can right now take a look at our initial conditions. And this is very important. I hope you can remember last time when I explained to you the function of initial, or the role of initial and boundary conditions. The initial conditions are like the starting solution we use for our iterative approach to solve these equations numerically. And in contrast to an incompressible simulation like we did last time, we have absolute pressures here. So therefore we have initial value of 1 bar. For the velocity, we don't will touch it because we don't know anything, or this is the best start solution we have from our experience. Temperature is also fine. This is the environment temperature, and now dynamic viscosity. Here we will use this value, which we can calculate based on pressure, on density and kinematic viscosity, for example. And now we will add 8 for K, 8 for K for the kinetic turbulent energy, and 50 for omega. And this values, this is important to understand this. Basically, K and omega are calculated for the whole flow field. Only for the inlet we know K and omega because we can calculate it. There are several formulas out there you can use. If you're interested in this, I can post them also in the forum. But basically, what you do, you only need your Reynolds number, and out of the Reynolds number then and some other parameters, you can calculate K and omega very easily yourself. And what is happening is that we use this as initialization for the whole fleet because this is makes sense and will help to reach a fast convergence. And later on, when assigning the boundary condition, SimScale is automatically taking this value to calculate the right turbulence model boundary condition for in and outlet. Okay, and turbulent thermal diffusivity, we will not touch this initial value. Now let's proceed with the boundary conditions, which are in the end describing the interaction between our model and its environment. And let's start quite easily with the symmetry. The type is symmetry. Call it symmetry. Makes sense, right? Then for the aircraft itself, and now we can use our topological entity sets. It's a wall, and it's a non-slip wall for sure because we have it's a physical wall, so there's friction between the air and this wall. And the only thing we have to define, we ask for, is the temperature here, and the temperature will put set gradient to 0 because we don't know the temperature distribution. The only thing we know is that here on the aircraft wall velocity is 0, everything else we don't know, so therefore we put gradient to 0. Next boundary condition we have to add is for the inlet, and this is a little bit more complex than you may first saw because especially for compressible simulation, you can really become convergence problems for high inlet velocities. And there is a very smart trick that calls ramping. That means you are not starting with the full flow velocity. you want to simulate, you start with a smaller one, and then you can step by step with every iteration increase this value, and this will damp numerical problems and help you to reach a fast and better convergence all in all. And therefore we change to file upload, input type, and then we can upload an Excel sheet, which you also will be provided with, to which will control how the inlet velocity is changed. So upload file, let's call it VRAMP. Then we just have to sorry guys. And then we have to change this to 1. It's only dependent from time. And column index is 1, is 2. And if you take a look at this, this is the content of the CSV file. So column 1 is 0 and 700, that's our iteration, and this is the flow velocity. So we start with flow velocity of minus 50 meters per second and increase it to minus 116. And here we have to add now column 4, but it depends how you import this, so comma separated or tab separated. Great. And for the temperature, in this case, we know the temperature, it's a fixed value, it's environment temperature, and we apply this on the inlet. Yes, the boundary condition for side and bottom, or for, let's say, all the other walls, it's also quite easy. So let's select side, top, bottom, and the type is a wall. A slip wall in this case. And here you can see, by the way, you choose between wall function and zero gradient. By default we're using wall function, and this wall function will help us to have a better representation of the boundary layer. And here again we know the temperature, it's environment temperature. And we are done. And then we have only one boundary condition missing. It's the outlet. Here we don't have to ramp anything, so we just choose type pressure outlet. Yes, this is the pressure we want to have as the outlet. It's fine. Click on save, and we are nearly done. There are just 3 more things we have to do. First of all, we have to update our numerical settings, because these settings were are much too high, and this is quite complex to understand. So if you're really interested in this, you should consider our documentation or join our professional training, where you can learn more about this. But in the end, we will just adapt. Relaxation is nothing more or less than a factor which describes how conservative you want to calculate. Value of 1 is neutral, smaller than 1 means faster convergence but less stability, and larger than 1 smaller than 1 means less convergence speed but much robustness, and larger than 1 means more convergence speed but less robustness. And here I will just update these values. Especially density is very critical. Then we will use 2 correctors. Correctors in this means that they are used to correct nonlinearities or non-orthogonalities in the mesh. We will use cell number 0, so every cell has a number, and with a reference pressure of 1 bar. Okay. Next thing we have to update is our absolute tolerance for our residuals, and there we will change the value also to increase stability and accuracy of our simulation. And oh, I forgot about this one, I think. Yes, for all our transport properties, maximum density is fine. And now we have to choose the right solver. For pressure, we'll use a GAMG solver. With a much higher relative as well as absolute tolerance. And we will also modify, for example, we'll have pre and post sweeps to increase stability of the result. And then we will update all other solvers to smooth solvers. And this looks really weird, but don't worry guys, we'll provide you with a step-by-step instruction what you have to change how. And what we have also seen is we'll use symmetric, Gauss-Seidel, etc. Great. Finally, we'll just change some schemes. Schemes describes a way we are, for example, calculating divergence or other operators, and we will change everything possible to bounded Gauss upward because that is more stable. On the other hand, it needs more computational capacity, but this is okay in this case, I think. Great. Now we just have to define simulation control. That means in our case, we want to perform 1500 iterations. We only want to save the final result and use 16 cores with a maximum runtime of 30,000 seconds. And finally, we will add a result control item, wall plus, so we'll activate wall plus calculation. Yes, now we can create a new run and start it. Great, then let's do a wrap up of this stuff we discussed right now. Sorry guys, I know it was very exhausting and took a lot of time, but I think it was really important to show you this first steps. Yes, and so we saw the general mesh setup and mesh assignment. We created again topological entity sets, defined the material, and modified initial boundary conditions and numerics. And since calculation takes a lot of time, for sure I have prepared something. So here is a project including the final simulation result, and now we can take a look at the results themselves. So yes, once the simulation is finished, I've created two runs, one with y plus, one without y plus. You get this convergence plot, which is looking quite nice. And then you can switch to the post-processor and open the three-dimensional simulation results into the online post-processor. And that can sometimes take some minutes since all data have to be loaded into the post-processor environment. Guys, by the way, since I think there'll be a lot of questions, you can already start to write your question into the question box and I will answer them just after the end of our demonstration. And here are our results. And first of all, we will only import the internal mesh. We automatically in the latest simulation time step. And the first thing we will do is add a so-called cell data to point data filter, which is necessary for incompressible simulations to have interpolation between the cells. So right now this can take some time, again like 1 minute, because you have to like interpolate in this case more than 3.5 million values, but it's done. And don't activate this pass cell data option, because we don't need the cell data. That means that we will only have point data in this filter. Yes, and once this is done, we can already start to do our post-processing. And the first thing I want to create is a slice. And here it's important to put the slice under the cell data, point data filter, not under the run. And as you know, I can define this slide by giving a normal and the origin. So I will define this normal here. Don't want to see the plane, and I will hide the internal field. And yes, you just have to wait some seconds, and then the slice is calculated automatically. But since yes, and this calculation of the slice can take some time, but it allows you to have really a deep look into the flow field. So let's zoom in, and right now we are visualizing the pressure, for example. And now you can see the pressure distribution in the symmetry, and you can automatically rescale it. But beside pressure, for example, velocity is much more important. So let's take a look at the velocity distribution in this mid-plane. You can let's show the legend, and let's change it back to 65 meters, for example. Sorry. So here you can see now, for example, the wake behind the aircraft, and you can also take a look, if you want, at the density. Here I think we don't need the full range, so 1, 2 till 1, 3 is fair enough. Oh, it's still pressure, not. No, it's density. Then you can see the change of density, and for sure, what you can also do, let's go back to U. You can also move the slice wherever you want. For example, we can go like 1 meter in X direction. Or even more, for example, if we want to take a look at here, the wings. Yes. Okay, nice. Next thing we will do is add again the solution field or the result to the viewer to visualize the surface of the aircraft instead of the external flow field. So we have just to wait for a second until it's added. And yes, then we can easily also take a look at other stuff, like for example surface pressure distribution. In the meantime, I would like to answer a question. William has a question. He wants to know if some divergence for the calculation is the reason of the servers we are using. No. All our calculations and data and executables are saved on encrypted hard drives, and we are quite sure that, and we know that we can reproduce the results independent from when you start the simulation, so you don't have to care about this. Next question is by Otto, and Otto wants to know if it's possible to view the setup as a text file like an open form after the setup of simulation. Yes, Otto, that's possible. For this, you just have to create a report. Let me show you that later on. In the end, you just have to click here to report, create a report, and then all settings will be listed in a text file on a PDF. Okay, now we've imported the next project again, and now instead of importing this internal field, we'll only import the faces of the aircraft. Apply properties. And then we can show it again. Hide the slice. And now you will see the geometry, surface pressure distribution on the aircraft itself. And we can also take a look, for example, at y plus values on the surface, so of the first cell. And here, for example, let's scale it from 30s to 500. And then you can see that for some regions, y plus is not perfect, so we should even make the elements flatter. But this is for the first simulation, it's really okay. And what we can do also is, for example, create streamlines. And here is something very important. Let me delete the filter again. Again, use the point data because they have higher accuracy. Add a stream tracer. And yes, we already created streamlines. So in the end, you have again to specify a point source. For example, let's do some streamlines in front of the nose. Turn this back to solid color, then we can, for example, now we can color the streamlines by the actual flow velocity, and we can even add in, for example, additional streamlines. Let's say to visualize flow at the tip of the wing. And what we also can do, what is very helpful, is to create so-called isosurfaces. For this we add a new filter called contour. And let's imagine we want to visualize turbulence around the aircraft. Then we apply this filter for turbulent kinetic energy. Add here, let's say 190, and now all surfaces, or we will create a surface, a closed surface, which has a constant value of k of 190 on its surface. And for example, now we can make this turn this to velocity. And if we make it transparent, we get a really nice image. And you can create such contours for sure also for pressure and all other scalar values. Here. Great, then I would say we are even done with post-processing. I showed you how to create slices, how to create streamlines, isosurfaces, and to visualize surface distribution of pressure or Y+. And there's some additional stuff you can do with our online post-processor, like creating plots or using the calculator to derive your own physical quantities. But this is something you can really learn playing by doing. Guys, thank you very much for all the time. Now I would like just to show you your homework. Your homework will be to perform this aerodynamic analysis for two different setups. One is to simulate, let's say, free flight, and one is to simulate a plane in the near of the ground, where we have the so-called ground effect. And you should create the simulation for three different speeds. So in the end, it's about creating two meshes, or the modification of the mesh is very easy, and to create for each of these meshes three different simulation runs. You will find all resources you need on our website simscale.com/EUROAVIA. Here, for example, you can already find submission form for homework, the tutorial, and in the forum where you can also ask all your questions. And besides the submission and your question, for sure, we would love if you would post your nicest or submit your nicest post-processing image. And if you want to discuss about the results, we would be really glad to have such a discussion on our forum. Okay, then. We made it, guys. Thank you very much for all your time and staying so long in the session. And now it's time for question and answers. And the first question is by Alex. And it's not a question, he just says he liked our workshops. Thank you very much, Alex. It's a great pleasure also for us to host these workshops, and it was a lot of fun for me. I hope you also enjoyed the session. Guys, are there any more questions, or do you really need a break right now? Okay, seems like there are no questions. Then let me say thank you very much again on behalf of the whole SimScale team. I would love to see your homework. If you have questions, if you have questions, just use our forum or send me a message. And for sure, please send us also your feedback, positive as well as things we can improve. Whenever you need me, you know how you can get in touch with me via email or the forum. Thank you very much, guys. Have a nice day, a great weekend, and hope to see you soon on our next workshop. Bye.